Okay, here we go. Last lecture before the annoying spring break. Homework, I'll get you out today, something like that. So some assignments to be done, but you'll get it. Any other things to tell? Not really. So I need to tell you a little bit about robot components. The signal processing, I don't think we'll get to that today, and that will be another lecture at some point. Hardware of robot is incredibly important. Hardware, software systems, sensors, actuators, the physical principles, how they're done, how much money you spend on them, to be quite honest. All of this matters tremendously. Let's see. What is a decent robot? What's the cost of a decent robot these days? A decent industrial robot, at least a couple of $100,000. Just one of these, not Puma-like robot. You've seen that picture of this very old one, but the more modern one. Big manufacturers like KUKA in Germany. Who's doing robots in the United States? Big industrial robots. Actually, I don't know. The Japanese have lots of robots as well. So a lot of money, quickly up to millions, so it's a big investment. A humanoid robot, the one we have in our lab, which you saw when you did the lab, it's $1 million. That's a prototype robot, so that doesn't really count because it's produced in very low quantity. That means single quantity. Research robots, usually just to have an arm which is decent, a decent one start with $100,000, $200,000 quickly to have something decent. And well, the now robot you've seen, it's a $10,000, $12,000 robot actually if you buy it. It's also a fair amount of money if you think about it. And this has now been produced in larger quantities, so that's not so single production anymore. And still it's very expensive. And that's actually a very mediocre robot from a research robotics point of view, since it's too much plastic in there, too much imprecision, nothing we can work with. Who of you has ever played RC cars or RC toys? Remote control toys. You know a little bit? Okay, remote control toys is actually also a very basic robotic system if you want to. So just reminding you, so normally if you have a remote control, I don't know what it looks like. Let's take one for an airplane which looks like this. Usually has some sticks here which you can use with your thumbs to control the thing. Has an antenna. Then there's a little receiver on the airplane or whatever. It's a boat, an airplane, there's a receiver. This is just for the remote control stuff, which then can basically, depending on how many channels it can actuate, put something to little steering servos, which looks like these. These are motors which just they take a rudder up and down, or they go to a big motor, which then basically drives the wheels. So these are very terrible pictures, which I'm going. But all of these things are basically, this is a motor which is basically combining sensing and actuation in one thing. It's just a gearbox. We'll talk about this a little bit. And this is just actuating a motor. Actually, you never go directly to a motor. You go to something in between, which is a kind of a motor controller, often called an ESC in the remote control world, which basically converts a low voltage signal, a steering signal, into a high current signal for the motor. So these are typical things. This is not so unlike what we have in big robots, just we have it in a more elaborate way and more complicated way. You ever played those things? So my kid has them, so I'm currently totally aware of everything in this world. The more money you spend, the better the stuff gets. And that is the same for robots in grand general. In building low-cost robots like the now, you have to sacrifice something. Like, have you guys heard of the Baxter robot? Yes, maybe. Baxter is a 1- or 2-armed robot, and I think it's 2-armed originally, which kind of the founder of the iRobot company, which is the Roomba robots, Rodney Brooks, tried to create a couple of years ago. And it's a low-cost robot for just about $30,000 to $40,000 with 2 arms, which is supposed to do simple manipulation tasks. It looks pretty much like it's a failed investment. It's not a very good robot. To be honest, it's too cheap. You cannot really build a decent robot for $30,000 to $40,000, which then lasts in an industrial environment for more than 2 or 3 years. So, kind of complicated. So, the beginning of that lecture is essentially that robotic hardware is cool what we have, but still incredibly in its infancy, to have something which is super reliable and which we can put together to make cool robots, reliable robots, long-lasting robots. Some exceptions exist. So we have actually, in my lab, we have 2 robot arms. You must haven't seen them. The hydraulic arms. They are on our webpage, at least. And I've had them for 20 years. And I turn them on, and they still work. But each of them was about $500,000. So maybe there's a reason for that. They're fabulous. But this is kind of the ballpark of money you have to spend. Now, this is all fine. In research, a couple $100,000, quote unquote, are not that important. Most of the time, most money we spend is on people. For industry, if you want to be profitable, it's a huge investment. Yeah, how long does it take you to break even if you make an investment in $500,000 worth of robotics, and you have to maintain it, and you have to hire some people who can A, program the darn thing, and B, maintain the darn thing. So that becomes more complicated. So I want to talk about all the components of a robot. So just giving you an overview. This is kind of a very low-key lecture in so far. I just tell you about stuff. If you have questions, ask questions. Questions are always good. So let's start with power supplies. And you can just go through, just enumerate physics. What can you do? You need some primary power. This is either electricity, or it could be hydraulics or pneumatics, or it could be mechanical if you want to. So mechanical is not used very often, but you could create something. Remember, so in the good old days, there was your home, where you live. And then there was a hill. And then there was a river coming by, running down the water, and here you had a wheel. The water went over the wheel, it turned the wheel, and splashed away. So that's a nice way of creating mechanical energy. So you need some weights. It's still kind of some. So do you know the PR2 robot? Some of you have seen the PR2 robot. Some of you, I'm sure some of you have worked with it. The PR2 robot is a kind of a personal robot like this. Has 2 arms like this. This is a terrible picture in a head, but just like this. In order to make the arms weightless, it actually has counterweights. So it has a big weight in here to pull against gravity as much as possible. So it's very simplified. This is something with springs and weights. But that's some form of mechanical actuation. You basically use gravity to do at least the gravity compensation. Electrical power is for electric motors. Hydraulics is usually oil. That means you use a oily fluid which you push around. We talked about this a little bit. It's very popular in excavators and huge construction machines. It's not so much used in robotics because it's more messy and much more expensive to manufacture. But one of the most high-performance robots we have these days are all hydraulic. Pneumatic is air. Big difference between hydraulics and pneumatics is air is compressible. Oil is not compressible. So if you work with pneumatics, then you get some kind of dynamic effect from the air compression, which is annoying for many people. Mechanical, we just talked about. The moment you have power, you also need something like a power regulator. For electric systems, usually you have something like current control. It means how much current you let through. There's something which is called pulse width modulation. I showed in a second. In hydraulics, you have valves which basically regulate how much flow can actually go through. So there are different principles how these things are done. In the end, everything goes down to some kind of electric steering on electric components. Since even a hydraulic pump in the end has to be plugged into the wall and draws a lot of current. But it's what we would call the primary source of power. It's basically what really makes the robot move. So let's look at some of those things. So these are typical hydraulic pumps. They're usually that big. They weigh about 400 kilograms. They are super reliable. They're built for industry. Obviously, they're not very portable. You could make them portable, but you need a truck for that. So we have basically in our robots, for the humanoid robot, we have one, and for our other robots, we have one of those as well. They're put in the closet. They make a fair amount of noise. It's something you worry about as well. Okay, how painful is it to work next to your robot? How much squeaky noise do you get? Do you need ear protection? You don't want to work in an environment which is very noisy in general. Super reliable, work really nicely. The main thing about hydraulics is actually the big box has a lot of oil inside, usually like 20 gallons or 25 gallons. And one of the key principles of that system is that they cool through the oil reservoir. Very important that the oil gets very hot. So you quickly go up to 100 to 150 Fahrenheit or make it 40 to 60 degrees, 7 degrees Celsius operating temperatures, and that needs to be cooled away. So this here is actually a heat exchanger. This is you connect it to water, and then you have basically water cooling on those systems. And the heat out of the robot comes to the oil, and the big oil reservoir gives you kind of a steady temperature regulation. You can build much smaller hydraulic units, which are like this size, but they have then just a gallon of oil inside, and the cooling becomes much more complicated. You need huge fans and cool it down in a different way, or you need also water. But usually if you want to make them portable, you want to also have everything portable. You don't want to connect it to water hoses. And so you put fans on it with a battery and then cool them down this way. Here is one of the important components. You can read that, but I'm not going to go talk to this. How people regulate electric motors. It's very simple. It's called pulse width modulation. And the idea is essentially, if you have, this is here's time, this here is voltage, or it's V of t, I guess it's current. If you say have 1 volt, which you can use, or negative 1 volt, you just turn your voltage, your source on and off at certain intervals. So here it's on, then it's off, on, off, and now reverse direction. On, off, on, off. You can imagine, okay, whenever it's turned off, nothing's going to happen, no current is going to flow. When it's turned on, current is going to flow. So depending on how thick you make these pulses and how quickly you space them, you can essentially modulate the amount of current which is flowing through this little circuit which turns stuff on and off. And that is called pulse width modulation. So basically, usually you clock these pulses at a certain frequency. This is here irregular, which is kind of odd. It should be all the same. And then you modulate the width of those pulses. And if you basically make it all the way open, then you would have a constant, which you basically current flow, the max current flow you can get. That means you're going full blast. If you turn it all off, here's nothing. Usually there is a little device which does that. So here, fine, once upon a time, a long time ago, I built that robot. Cool. But it's still a very valid robot. It actually has all the components which work and which don't work on some robots, like for instance, strings coming off. But you see 4 electromotors inside here. You can look at it, you can pass it around. And on the back, you see actually little crummy PC boards. They do pulse width modulation. That's exactly what they do. They basically get from a computer these pulses, which are very low voltage and low current, and basically translate them in some heavy current flow for the motors. So it's some kind of an amplifier board. If you want to pass this around, feel free. You drop it, you get hurt most likely. Okay, so that is also which happens in many of the RC cars, for instance, what the ESC is doing, with this little amplifier for the motors. That's the same idea. Hydraulic valves. So what I showed you was just how to regulate electric current. This is basically, for instance, how to regulate a hydraulic flow. It's in essence super simple. So this is one way of how this is realized. This is a cut through a hydraulic valve. It's usually about, it looks like this. It could be in a size like this, basically not very big as a component. And all what matters is essentially that here's a source of oil and here's a source of oil coming in or out. And then basically you can flow this way. And what you're doing is you have a little tube here which you can, with the help of some electric motor, can basically bend upward or downward. And that basically says the flow goes this way or this way. And if we now put this into a simple picture of a normal piston, actuator, which would look like this. And hopefully this is a little bit better built since it needs to be sealed. Then we have some possibility of getting oil in here and then oil out there. This is one direction of flow that would move the piston to this side. And obviously I can turn this around. And that would move the piston in this side. And so all what I need is something which can basically regulate the flow in one or the other direction. So this one channel would go to here, the other channel would go to there. And by bending that little tube up and down, I can basically regulate the oil flow. Very straightforward, very simple. Doing this right and building these things turns out to be quite expensive. So a good hydraulic valve is in the order of $2,000 to $5,000 a piece. There's incredibly high precision engineering in there. These things run at pressures of about 210 bars, or in the funny units which we're using here, 3,000 psi. And if you wish to relate to that, what should you do? You need to go diving somewhere where you can go more than 1.5 miles deep. And you can try that, and then we come back up and we look at you how you look like. You should be solidly squished, since you're not built for that pressure. So most submarines cannot go that deep. So if you see all these kind of cool submarine movies, they all start getting into solid trouble when they go to 1,000-meter depth or something like that. I think the best submarines, but they're unmanned submarines, can go 5, 6, 7 kilometers deep. But normal standard submarines cannot deal with that. So going something like 2 kilometers deep, which would be roughly 210 bars or 1.5 miles or something like that, is a huge amount of pressure. Now, this amount of pressure you channel through all these little valves. So they have to be solid. Otherwise, they just fall into little bits and pieces. And that could be potentially dangerous. So what, for instance, in our robots, what happens is if you have a robot arm, like this, interestingly, they drill holes through the metal to get the oil to every point. This is expensive if you have to drill long channels like that. Particularly, the drilling of curves has still been a big problem in life. That means instead of doing a curve, if you have a piece of metal, obviously you have to drill in here like this, and you have to drill in there like this. Connect them. Most of the time, they actually drill all the way through and all the way through, and then they put little plugs in here. Hopefully they do it right, since one of these plugs comes loose with 210 bars behind it, it's like a bullet in the lab. Hasn't happened so far. But it's an interesting, you're just working with incredibly high pressures throughout the robot, and it requires a fair amount of high precision engineering to do that properly. Let's see, what else is there important? This is just a typical actuator or control diagram for a hydraulic system where there's something like, again, a little control system, the servo controller, not unlike what you have on in an RC car. It basically tells the servo valve to go left or right, and this basically moves the actuator in the correct direction. Then you have your joint moving, and you have some feedback control, of course. And the servo valve lives from the big hydraulic supply, and things are happening, hopefully, appropriately. There's interesting components, again, in hydraulics. Pneumatics is the same thing. If you make your holes here too small, you get actually fluid dynamics effects. And suddenly, despite you have a huge amount of pressure, actually the fluid cannot flow fast enough anymore because there's too much friction in there. So these kind of things matter. If you make them too big, you need too much oil flow. You don't want too much oil flow, since a pump usually a big 10 gallons per minute flow. That is good enough to get one humanoid robot going, roughly. But it would be nicer if they could do much less. Actually, a very interesting component of hydraulic valves is that even when they're standing still, there's what is called an idle flow. That means there's about 3-4 gallons a minute in a humanoid robot, which is just flowing for the heck of it, just keeping everybody happy and cooling things, which is a used waste of energy. So hydraulics so far is a terrible waste of energy. Okay, you can read these things these days. This is just what is in our hydraulic robots, the control diagram. Looks cryptic. Not so much if you would really go through it for a second. So if you start at the right moment. So here's a 1 degree of freedom joint. And here's the hydraulic valve. Then through this channel comes basically how much current is given to the hydraulic valve. That means how much it's going to be bent. And the rest is just signal processing, so forget about all that stuff. You can leave this out. It's just coming in a convoluted way. Here's actually the computer. It comes in here, sends a torque signal to the system. It's compared here against the load cell coming in there. So that here's a measurement device which senses force or torque. Then you compare it, and then it runs somehow back there, and you just have a regular P controller-like system, or PD controller, to be quite honest, for controlling a particular torque. So this is not actually, forget about this, it's too low resolution to really see properly, but what is important is this is a active regulation system for a hydraulic system, such that it becomes and feels like it were compliant. We talked about compliance the last time, so that it gives in. And that is exactly what it's doing. Having the load cell here, and I say I want 10 Newton meters at this point, then the hydraulic valve is generating some push to the actuator. It's measured how much torque it's generating, it's compared, and then regulated appropriately. Depending on how you make your P gain, you make it very stiff, then it will be a very stiff system. You make it soft, then it will give in. So that is the typical active compliance system which is used in hydraulics most of the time. Otherwise, hydraulics would be stiff. In excavators, it's not used. On a decent robot, you have to put this in, otherwise you're just like a rock. Okay, so lots of pictures. What do we have about actuators in general? So pros and cons. Let me see what comes next. Electric motors, hydraulic motors, pneumatic motors, these are kind of the most typical things we're using. Most people prefer electricity because it's clean, which is nice. No mess in the lab, no oil spills, no nothing. The problem of electric motors is that they're either heavy, so that is, if you want to build an electric motor which can create a fair amount of torque, then usually they become big like this now, realistically. So 1-to-1. This is what is called a torque motor. It would be a motor which can create a really big torque without any additional gearboxes or something like that. The alternative is to create tiny little guys. So if you look at that robot which goes around, it has actually tiny little motors in there, and then has a gearbox on top. And inside of the gearbox is basically a transmission system which basically makes that very high, fast-moving and very low-torque motor feel like a slow-moving but much higher torque system. This is all very nice. This is a great principle to basically take a simple, small part and make it really strong. But it has the disadvantage that this gearbox here adds a lot of friction in components. If you look at a gearbox, so all of you have seen gears at some point, and I also have some pictures at some point. So let me try to draw a gear. Okay, almost beautiful. Usually meshing with a smaller gear. Let's make a small gear here. Okay, it looks like sunflowers, I know. Okay, so you have this inside there. Just you make the number of gears with the small guy and relative to the number of gears of the big guy is what is called the transmission ratio, often quickly going from 50 to 1 to maybe 500 to 1. And an interesting component when you do that is you're also magnifying, when you're magnifying the torque of the little motor, you're also magnifying its inertia, and you're also magnifying all kind of friction properties inside. Suddenly, something which, if you do it as a little toy system like here, would just mesh and move very smoothly. If you have these high transmission radios, it is very, if you turn the little gear, it's fine. If you turn the big gear to move the little gear, it's hardly possible because so much friction inside. Now that has the problem that if someone comes from the outside, so this is called what is called backdrivability. So backdrivability means you can come from the outside and push. So what he's currently doing with the robot arm, he's actually doing backdriving. He's basically pushing that robot, which works fine, since that is actually a transmission system which uses gears and additionally these pulley systems, which is not, doesn't create so much friction. The motors in there just have a, I think, 1 to 10 or 1 to 20 transmission in the little gearbox. So that's still possible. If you have it 1 to 500 or something like this, you would not be able to move this anymore from the outside. You can only move it from the motor side. The problem with that is that if you have an impact with the environment which is unanticipated, then you're stiff. You're actually as stiff as hydraulics. So you need to either get a active giving in system, or yeah, I don't know, or you're just stiff. And the worry then is these two things are actually only connected by a few teeth at a time. And you get an impact in this, you know what you get? A gear which just has a few teeth left, like this. The rest is gone. And that's very easy to do, actually, with gearboxes. You can even do this in your little RC toys, and they have little servos, and you would overload them, and then all the gears are gone. So backdrivability is something which we care a lot in modern robotics, about robots which go out in the world, which interact with the world, which can basically impact the world, and which should not break. So people have to put something in. Sometimes then basically what people put in there is, instead of having this here directly connected to a joint, so this is now my robot arm. Here, I can make a hand on it for you. I could put a spring in between, so that when there's an impact on this joint, first the spring will give in a little bit, and then the gears have to be pushed. That helps to take the major impact away. It gives you the misery that you now have a flexible system, a spring in there, so that your entire rigid wire dynamics, as we know it, is not correct anymore. There's another differential equation which comes from this stuff. And you would have to model that in order to control it properly. Okay, so we have electric motors. They're either heavy or they're light with transmission boxes. They do need some amplifier, like pulse width modulation, like the little PC board you've been seeing there. But then they're easy to work with the moment you have that. Just building an entire system which is nice and works well is not so trivial. I should show you some videos at some point. Oh God, this thing has given up again on me. So annoying. Let me see whether I managed to pull up a video. So let me see if I managed to do this. Here we go. So that is actually an electric motor system built by a Japanese research lab, which called themselves Team Shaft. It's kind of a strange name, but it's fun. Let's make this potentially bigger. And this is just a very fast summary of what they did with this robot, walking up the ladder. This was the DARPA Robotics Challenge in December last year. And they basically built some very special electric motors in there, which are not too big, but bigger motors, so not quite the small ones. The gearboxes, which are called harmonic drives, it's a special form of gearbox. And they actually use water cooling for their motors to make them stronger. And so that's actually a very special concept to have water-cooled motors. So all the stuff which you see coming in and out of the robot is not just electricity, but it's also a cooling system. don't get your hopes up. This is not autonomous control. This is remote control by an operator who sits in a dark room. So the idea was that the operator cannot physically see the robot, but can only see what the robot is perceiving through its own cameras and whatever. So we haven't solved robotics yet. Okay, oh, here's more of it. The red version. But very important, so this thing is, in the end, impacting or working in a dynamic world. And it is protected by appropriate systems that the gearbox that it has and the way it's built, that it can take these impact shocks. It looks like some alien from outer space, to be quite honest. Well, if you want to see the cool hydraulics component, I don't care about Google buying stuff. I don't know why that is now suddenly on there. Can we just move on? Okay. So that's a hydraulic robot with onboard power. That's what it is. Boston Dynamics has been really good packaging this all together. It was meant to be a cheetah, okay? So that's fine. Again, very important, this is hydraulics, okay? This cannot work unless they put active compliance regulation into the system. Otherwise, it would not be elegantly going like this, we could fall over, we could sit at the wall. Okay, if you don't have compliance, this thing would be broken into pieces. There would be nothing else. Okay, so fine. They also have a humanoid-like robot, so this seems to be a nice scenario. This was a space, like a spherical feature. They have really nice walking. There's not a person inside, it's a robot inside. At least I hope. Good. Yeah. But it's created some good robotics components before you do that. That's the big dog robot. Right now it's not powered to the that is an important task. Okay, fine. Please subscribe. Okay, fine. We won't do that today. Cool. Just wanted to show you a little bit. Fine. So now you saw essentially hydraulic stuff. Hydraulic motors are very lightweight. They're actually just pistons and very simple things. Problem is you need a pump and a power supply for that, which normally is done externally, but what you saw in these videos, if with an appropriate amount of engineering, you can get them on the system. Now, fine. The secret, not to be disclosed knowledge, is the energy efficiency of big dog. So the thing which was throwing the rock, is worse than a Humvee. It takes about 1 gallon of fuel per mile. So that is terrible. We always thought the Humvee is really bad. A Humvee is about 4 to 5 gallons per mile. No, the other way, 4 to 5 miles per gallon. So energy efficiency is completely pathetic. People have to work on that, but that's not necessarily research does, one step at a time. Hydraulics is messy if it breaks. Otherwise, it's beautiful. It's very strong and can be very, very fast, and that's what you saw actually in the last 2 videos. And it's very expensive to generate. And then is the stepchild of hydraulics, pneumatics, which would be so nice. You know, in industry, there's a lot of industrial automation with actually pneumatic things which open, close. You have a psh, 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 psh. You've seen maybe these kind of factory pictures at some point or videos. Pneumatics is great because it's essentially, it's lightweight, it's clean, it's compliant, which is also good, so it's shock resistant. You need a compressor, this is the pump. It's not very strong, and the problem is it creates all these dynamics which we don't understand. So people have been trying to create pneumatic robots again and again and again, and then have always stopped again. The current, I think in the market, there's one system which is called the shadow robot. It's an arm with kind of muscle-like actuators, which are pneumatics. So the idea of a pneumatic actuator is actually, there's my pen, it's incredibly simple. You basically take something like a rubber tube, close it up on both sides, and then you pump air into it, and it bulges like a muscle and becomes shorter. That's it. So that it doesn't burst, you usually have to put a net around it so that it kind of basically doesn't become like a bubble or like a balloon and flies away. The problem with these things, as you can imagine, they pop a lot. And I know that there's lots of labs which have things like that, and they change muscles all the time. So it's a little bit annoying. Yeah, the dynamics of pneumatics is the biggest problem, so that the aerodynamics, the compressibility is extremely hard to control, and it's very hard to get decent and accurate control out of these systems. So nobody really uses them in decent research robotics. Again, there are some experiments with some companies, but it doesn't really go so far. Just if you ever wanted a checklist, what you want from an actuator, you want low inertia from the actuator, so the actuator itself shouldn't weigh a lot. It's nothing more annoying if you have big motors like this and you try to build an arm. So first you start with the shoulder. That was easy, so I put the big guy in there. And I need a big guy in the elbow. Oh, because I have a big guy in the elbow, my arm became so much heavier, and I have to have a bigger guy in my shoulder. Now just imagine if I add the wrist to the story, and it gets even worse. So if you build things from electric motor, where you have to carry these components at the very far out components of your robot, it means you propagate a huge amount of weight to the far away, or to the motors close to the body, which is a problem. So in essence, you want something which is really low inertia, as the system itself should be lightweight, and also all moving parts should be lightweight. You want a very high power to weight ratio. That's obvious. The more oomph you get out of a small scale system, the better it is. You care about high acceleration. You want a wide velocity range. And again, acceleration and velocity don't go hand in hand. I can create a hydraulic system where it has very thin hydraulic tubes for the fluid to go through, like this size, literally this size. And it has great acceleration, but the moment it needs to accomplish speed, the fluid flow gets throttled through these hoses, and then you don't get velocity anymore. So these things are not going hand in hand. Just saying you have high acceleration doesn't mean you have high velocity ranges. You want to be robust to overload, so someone pushes you from the outside, you don't want to brake. You do want positioning accuracy, very important, and you want smooth motion. So in some torque motors which you have, or some gearbox system, you can actually feel the gears, how they are meshing, and then you get vibrations. And then you look at your velocity traces over time of a moving degree of freedom. So this is velocity, this is time. And you want to do a sinusoid which looks like that. It turns actually out to look like this. And you can see the freaking teeth meshing along that line. And depending how big that is, it can bother you, since you put this, and this signal goes as a feedback in a D controller, of a PD controller, and then you will see this noise amplified as a feedback torque in your system, and it's annoying. Okay. So far about actuators. Now transmissions. So let's look into that for a moment. More detail. Transmission is essentially what is between the motor and the degree of freedom you care about. So again, this is essentially this potentially transmission box which we have there. We usually use gears. That's a typical gearbox, which is also in your car. You can also use pulleys and belt chains. So this little robot, which I've been passing around, is actually good for that purpose. And it uses a mixture of both. It uses a little bit of gear transmission, like 1 to 10, to get more torque from the motors. But then it uses the pulley system to basically change the torque ratio again. And pulleys in these kind of strings are very low friction, and they're very nice. They're back drivable. So back drivability, if you know what that means. So what things do we care about? Back drivability, I mentioned already. Backlash is something which is really annoying. And the whole idea is essentially, let me do my gear stuff again a little bit more accurately. So here's one. These gears are terrible. So a good gear looks like this roughly. Okay, then it does a little curve, and then comes the same nice gear again. Okay. And then the other gear on the other side has to mesh in there really nicely. Obviously, I'm not even drawing this properly. So, cool. The proper way would be that this here is touching on both sides all the time. Very clean. So, full contact. Now, the moment you get actually from wear and tear some play in here, so that there's really a gap the way I've been drawing it, then that means when you go in one direction and you turn the other direction, you suddenly get, for a while, nothing before the other side hits actually the other gear and starts moving. That play component is called backlash. Okay, I used to have a really old car, a really nice old van. And when I was steering, it had similar properties. You were steering to the left, and then you wanted to steer to the right. It comes first, like for a quarter turn, nothing, and then I was steering to the right. So fine. As a human controller, you can get out of that roughly. It's a little dangerous. In a robot, if you do if you want to have here's my little robot arm again. I want to hold it at a particular position, like here. That usually means if there's a little disturbance force pushing me down, I have to push in this direction. Disturbance force in the other direction, I have to push in the other direction. It means I'm in a mode where I'm always going back and forth. The PD controller is always regulating back and forth a little bit. If you have backlash, it would be and you would get vibrations here as well. So backlash is terrible. It usually happens in gearboxes most of the time after you've been using it for a while, and this is there you will figure out how much money you spent on a motor and a gearbox. So for the first 1 month of usage, pretty much all motors and gearboxes will do the same thing. But then, if you spend the extra $500 on a fine Swiss gearbox and a fine Swiss motor, you will see actually the fine difference that you will not develop that backlash as quickly. There is actually a very cool transmission system which is called harmonic drives, which has no backlash. This is what most people like to use in big robots these days. And the idea is essentially something, I should actually get a picture, but I can draw it roughly. It's actually something which has a gear of the inside of a ring. And then it has something like an ellipsoidal thing here with gears as well. Just turning on the inside. There's another little ring in there which actuates that. But this kind of a gear system has always like 5, 6, 7 gears meshing at the same time. So it doesn't develop backlash as quickly. Usually people say it's backlash free. And it's called a harmonic gear. And it's used in most of the Japanese robots. and many other systems as well. It's expensive, these things, but they're really nice. So fine, properties of transmissions. You amplify the inertia of the motor. You also potentially amplify friction. You use these transmissions usually with electric motors. You don't use them in hydraulic systems. The hydraulic systems are strong enough. You don't worry about that. And you get transmissions up to 1 to 300, up to 1 to 500. People usually don't use more than 1 to 300, at least in robotic designs, but they could if you wanted to. Pictures. So typical, more nicer gearboxes. So big gear meshing with little gear. Here's a little gear. First, you usually connected to the motor, driving this entire system. This is often called a pinion. That's called the pinion gear. Is that correct? The little one is the pinion gear. I forgot. So typical gearbox. If you work with pulley systems, you have usually steel strings. They are wrapped in a particular complicated pattern to actuate the system and create you the transmission through this kind of pulley system. It's the same as what you have in a bicycle, okay? Bicycle, you have the big gear in the front and little gears in the back, and that creates a transmission system. And by swapping the gears in the back and in the front, you get different kinds of transmission, and basically you have to pedal harder or less harder or to go up or not up. Same idea here. The problem with these pulley systems is that the steel strings people are using, or these cables, are stretching partially. And you get unknown effects in those things as well. So they create some dynamics. So we have some robots in our lab, which are produced by Barrett. This is actually here from Barrett's webpage. And they can create, when the robot is stretched with a little bit of load, you suddenly get 2 or 3 centimeters inaccuracy just because all the cables are stretching, which is a lot. So there's pros and cons. The other con you've been seeing in my little robot, these things break and fall off the pulleys. And so you have to restring them occasionally, which is really annoying. How are we doing time-wise? Okay. So now let's go over to sensors. It was mostly about actuators so far. Again, the big guys in the market is usually electric motors, electric motors, electric motors. And then for some specialty people, they can work with hydraulics. It's a very small minority working with hydraulic systems. But getting a huge amount, after you have did the investment and know how to work with it, you get a huge amount of performance out of that. Now, what sensors do we have? In essence, you can say one thing. Robotics so far, or in the last 20 years, has been very much working with minimal sensing because it's cheaper and you don't have to create too many wires. So sensors have 2 components. One, how much does the sensor cost? How reliable is it? How often do you have to swap it out? If I put 100,000 sensors on a robot, most likely, even if they're very reliable, I may have to swap 20 every day. So you need to really see it a bit. The numbers make things more complicated. Let's see. The other thing with sensors is the wiring, which is really annoying. For every sensor, you need to run a wire to some of kind of a processing unit. Things have become better recently because you can put things on buses, so you don't need a separate wire for every sensor. Still, we have relatively few sensors. And comparing to our skin and our human body, which is literally millions of sensors, we just have like 10, 20 or something like that on robots, really little. But people work on all kinds of things. So tactile sensation is becoming slowly more popular. This is kind of some kind of skins. Proximity sensors have been around for a long time. This can be on little mobile robots using whatever. You can do infrared. You can do some echo sensors. Range sensors, usually laser sensors, been very popular. Then vision systems have become dirt cheap, and people use cameras everywhere, except you need processing power. What to do with the images. Position sensors are critical in every robot so that you know where your degree of freedom is. They come in linear and rotary versions. Velocity sensors exist, but are used very little, actually. Acceleration sensors are used much more. They are used particularly in IMUs, inertial measurement units. Measurement, this is correctly spelled. And these are things which basically measure on a system how much it is accelerating in a linear way and also how much it is its rotational velocity. These are also called often gyros, something like that. They measure what you have in your inner ear actually as a human being that basically helps you to figure out where you are in space and what's gravity as well, and things like that. Force sensors are standard in many robots. Often you can get things analog or digital, and you can get them as absolute or incremental. Absolute means that I turn it on and I know where I am. Incremental means it's a digital system. It can only figure out where it is by counting, and you need to give it a reference point where to start counting. Otherwise, you don't know where you are. So let me see. Let me show you first the picture. So these are typical potentiometers. This is things which most robots have for position sensing. So here's one of those typical, actually high-quality JDK $100 pot. They measure absolute position. Okay, you can turn them, and they basically give you a voltage back which is proportional to the position where you are. Not a particular big deal. They need 3 wires to go there, plus, minus, and the sensing wire. They come in all kinds of versions, big, small, but usually they can make them really small. You can actually make them super small. So, small is good. They're usually cheap, so $100 for a sensor is not too much. You can get them, what I have there is a rotary version. You can also get them as a linear version, which is like a piston which you pull in and out. And they give you absolute values, which is nice. You turn them on, and depending where they are, it's basically, how much time do we have? It's just based on resistance. It's essentially, if you have a resistor like this, and you have a little whatever finger which can slide along here in this direction, and you put some battery on this darn thing, and then you basically measure this here, the voltage relative to, I don't know, one of the other things, and depending on where this is, you basically, this is a resistive surface, you get more or less voltage out of the system. Very simple. The problem which you can see right away is there's a sliding thing, something which slides over a resistive surface, which creates mechanical noise and also mechanical wear and tear. So this is where the noisy component comes from. You have mechanical interaction, which is not great. You need to convert the signal which you get out of them, which is an analog voltage signal, into a digital signal, which is done by an A to D converter. It's not a big thing, but it needs to be done. The resolution is usually 12 to 16-bit. You can get higher resolution, obviously, but it's a noisy thing, so it's not what people like the most. The good thing is cheap and small. So this is what you typically get with every encoder you're getting. You basically say here is the degree, here's the position of the encoder. That is essentially how much I've been turning that little wheel here. And depending on that position, you know which voltages have. So that's the calibration curve. It's supposed to be a straight line. You would be surprised. They give you these straight lines, and then they say there's some 0.5% accuracy. 0.5% can bother you at some point if you want high quality accuracy. So you may actually say, I want to have not just the generic calibration curve for all of your JDK sensors. I want one which is for every sensor specifically. Or you may take it before you put it into the robot, you may run it through some test bed which gives you that curve precisely. And then that is what you put into the translation of for your computer system, which in the end has to translate the voltage into where you are. You don't want to lose accuracy through a bad translation. Nicer in life are optical encoders. So here, let me see pictures. Let me do pictures first. So here's a bunch of optical encoders. Here's one which I brought. It's about a $80 encoder. What you notice immediately, it's much bigger, okay? And you will see in a second why this is the case. It comes in various versions, smaller, bigger, depending on how many counts you have. You'll see this in a second. There are some very fancy ones which are super expensive, which is in thousands of dollars, but they come really big. Biggest problem is, right away, they are big. And having enough space to put these monsters everywhere is not so trivial. So what is nice about optical encoders? You can get them in very high resolution if you're willing to spend a couple of $1,000s. Otherwise, these cheaper ones that I showed you are lower resolution. You'll see in a second what the resolution means. Actually, I can draw this by the way. So how does an optical encoder work? It's actually incredibly simple. All you do is you create a disk which rotates, and you cut little slots into the disk. Okay? And you do this all the way around. And then let's look at the disk from the side. Well, then you take a little light bulb here and shine it through, and then you have some photoresistive system on the other side, which measures when the light gets through and when it doesn't go through. So it's very simple. It's like blinking with a flashlight. That's what this thing is doing. You can now see when this is turning, light comes off, on, off, on, off, on, off. So you get basically a curve when this turns, which looks like this. So this here is called off, this is called on, and this would be on. And if you can count the on and offs, then you know where you are, since you know hopefully at which position and how many of those guys you put in there. Now we get into the resolution story. So if I want to have a lot of those slots, I need a bigger wheel, like this one. This I think has about 4,000. Not quite sure. Maybe just 1,000. I forgot. If you make them smaller, you just have space for 100 slots or something like that. It means, okay, let's be naive. If it's just 100, let's make it 100 slots. That means I get for 360 degrees, I get only 100. I can only calculate increments of 360 through 100, which is 3.6 degrees, which is pathetic, okay, in terms of accuracy of position. Now things are not as bad, since you can do a little bit smarter than this, assuming the light shines through or not. You can actually look at the edges. When does the light go out and when does it come on? Okay? That means I can, instead of counting those guys, I can actually count those edges, which increases my resolution by a factor of 2. Useful. Okay? So if I have 100 slots, I actually get 200 edges and 200 impulses to count. So I can do a little bit better. But in the end, you're limited by that. Now there's tricks what you can do in order to get higher accuracy. And this is an annoying trick. Not sure whether it's useful. So here's my favorite motor. It's my electric motor with a gearbox. Okay? So motor, these are gears. Usually this thing rotates on the outside and I attach some kind of a piece of robot to it, which is I want to be moved back and forth. Now I could now measure against some encoder here how I attach this here. That has to be somehow connected against the solid surface. I could now measure how this is positioned by just attaching it here, aligning the two shafts, and then this here gets turned. Whenever this arm gets turned, and I know where it is. For that, I need something with high resolution, which is big. Alternatively, I can actually buy a motor which has also the motor side shaft sticking out, and then basically create my encoder here. Okay? Interesting. What's good about this? The good thing about it is my motor spins usually a factor 10, 50, or 100 faster than the side here. That means if I just have an encoder with 100 slots, let's just say I have a transmission ratio of 1 to 50, then that basically means I get a resolution of 50 times higher, which is 5,000 slots. This is good. So if I put the encoder on the motor side, I get much higher resolution without that I have to do a lot. If you actually look at my crummy robot, which I let go around, it had exactly that. If you look at this motor, the 4 motors which are in there, they look like this. They have a little cylinder in the middle, gearbox on the one side, and some encoder on the back side. So So that's basically how they are built. Now, this is all cool to some extent, but you give up directly measuring what you care about, which can be a problem. Most of the time, you want to measure directly what you care about, not something indirectly. Okay, so you get very clean data, which is really beautiful. There's no noise from mechanical stuff. You don't need an ADD converter, you need a counter, which is very easily available on most computer chips, but all these things are trivial. But counters are, again, very clean. When you differentiate them, what you get out of an optical encoder to get velocities is usually still a very beautiful signal. Cons is they're expensive or low resolution, they're bulky, you need some counting hardware, and they're usually incremental. That means you need to go to a specific start point. Just one thing which is fun to use, to know about, the way these encoders are built is actually they bump up the resolution even one more factor. And this is done with the help of what is called quadrature. So this is a typical encoder wheel, so it's called a slotted encoder wheel. And the interesting thing is it has two sensors, which are spaced a little bit with respect to each other. So it's not just one, it has two. And they are spaced, I think, by 90 degrees, well, 90 degrees, relative to one slot. So it means 1/4 slot distance. And the interesting thing is now, if you look at both of these sensors, when the wheel is turning, you get two curves. You get this one, which I've drawn before. The other one is just a little bit phase offset. Okay, not very complicated. But the good thing is now, if you have two of them, you can actually differentiate whether the thing goes forward or backward, which is otherwise a big problem. So you get this signature, so this one comes up first, then this one comes up. Then this one goes down, this one goes down. If you go reverse, it's not like this anymore. And this one comes up, then this one goes down. Then this one goes down, this one comes up. So from having two of these sensors, you know whether you go backward or forward. And on top of that, you get even more resolution. So now they're actually offset. That means I can count 1, 2, 3, 4 per every slot. So a decent optical encoder uses quadrature, which is a computer chip which does everything for you. You just get the two sensors out, and basically it gets 4 times more counts than it has slots. What is obvious actually from this picture or from all these things is you need to know where you start counting. When you turn the system on, you start counting at 0, which may be an arbitrary position depending where your robot is. So usually there's two ways how to do this. You run it against the stop and say you start counting from here. So it means you have a defined position where to get started. Or there's actually some of those guys which have what is called an index point. They have somewhere in the housing an additional sensor. When you go past that, it sends one more signal, which tells you where you are. And then you start counting from there, and you're fine. There's also absolute optical encoders, and they basically just have multiple of those rings here and just basically print a big pattern on it. That's it. And then you can, by basically reading out here where you are, you know what you are. You can obviously create more and get resolution as high as you want, just to get a bulky encoder, and you pay more money. Getting close to my end, hopefully. Quick thing about force sensors. Force sensors are really important in many robots, and they're a little painful to work with in grand general. So we want to know how much force or torque is generated by a motor. So again, we can have a motor here, we have the shaft here, we have here our piece of robot which we want to move. The question is, what is the torque being generated here? How could you measure that? In all of, not all, but most of our force sensing in the bigger robots is based actually at looking at something which bends a little bit. So the idea is, if I give you my favorite swimming pool diving board, okay? You put the really big guy here, then it will bend a little bit. What is interesting is if I look now at this bent diving board, and I would measure something how much the top surface stretches versus the lower surface, they stretch a little bit differently. And this kind of stretch, this deformation of the metal, you can actually measure. The way you do that is essentially, now let's look at this from top down. So I'm looking at this from this direction. You can put a little wire on there, like this, which changes its resistance when you stretch it. So if you make it, it gets stretched apart in this direction, its resistance changes. This is kind of the basic idea of what is called strain gauges. So they look essentially like things like that. These are very thin wires, okay, not fat stuff which I've been drawing there. Tiny little, very, very hair-like structures. You can arrange them in different ways. So this is what I just showed you before. Again, if you stretch them in this direction, they change the resistance that I can measure a very minuscule deformation of my metal. It's not a lot of deformation. I can arrange them such that I can measure torques directly. I can arrange them in multiple patterns to measure other things like shear forces. And they usually run through a specific electrical circuit to amplify the signal and basically measure it appropriately. These things have a few problems. So one of them is, for instance, that if you change your room temperature, they also measure something since they stretch a little bit. So you usually have one additional guy which is not in a stretchy area, which just basically reacts to thermal changes and kind of cancels that information. Okay, and basically these things you can literally buy stuff like this and glue them on metal with a special glue, and you start to have a strain gauge. Or what then interesting thing is, if you want to measure torque properly, then people build what is called load cells. Load cells are often very complicated mechanical structures. The idea is basically to have some piece of metal where one piece is deforming in a particular way with a strain gauge and everything else is not deforming, and you want them to be as stiff as possible. It's not that I want them to act like a mechanical spring. So some in our robots look very hard to draw for me. Let me try this. They look like essentially like a disc. And then there is a special structure on this disc, which is like a skeleton. Let's make it, yeah, like this. Wait, this is terrible. I don't know how to draw that. It's just a very thin rib which runs around, and the strain gauge is sitting on one part here and another part there. And then comes another disc on top. So the idea is it can only measure torque. It cannot measure any kind of forces which go in the wrong direction. So there's some engineering knowledge how to build these things properly, so that they truly only measure what you want. They have no thermal properties. They do not get contaminated by other things. A decent strain gauge, or I mean a decent load cell, if you buy it, is quickly $10,000. They measure then usually forces and torque simultaneously. You hardly get something decent under $500 to $1,000. So they're expensive little bastards, and usually need special hardware software to kind of amplify the signal. And still, what you get out of that, just over time, force looks solidly noisy. Okay? These are not pretty signals like optical encoders would give you. These are really noisy, annoying signals. All right. I think this is essentially it. So actuation, electric, hydraulic, big things with pros and cons. Gearboxes, backslash, backdrivability, very important concept. Sensors, position sensors are most important component. They come as analog or they come as digital sensors. You need to know what you have in your system and force sensing. Processing your sensors properly and right is the first thing you do in every robot. If you do it wrong, then everything is wrong from then ever after. So there's a fair amount of knowledge putting this together properly, examining it, having calibration curves, verifying that. If you have a torque sensor which measures 10 Newton meters, well, put something on which basically creates 10 Newton meters load and see whether it's really getting there. So when we get a new robot, there's a fair amount of verification of all sensors going on, which is annoying. Cool, that's it, and then happy spring break.